Hi physics students, so today I'm going to be recording a video reviewing the different types of motion graphs and how they look for different scenarios. So before we get to the different types of motion graphs for different scenarios, let's just review the two types of graphs in general. There's going to be a position versus time graph and a velocity versus time graph. So for the position versus time graph, what's on the x-axis will always be time, and what's on the y-axis is what depends on what time. So that's going to be the position. Okay, so when we're talking about slope of a position versus time graph, we're doing the rise over run. So in this case, for position versus time graph, if our graph is going to be time on the x-axis and position on the y-axis, the rise is going to be a change in position, and then the run is going to be a change in time. Okay, delta y over delta x. Y in this case is position, x in this case is time. If you think about the definitions of our different kinematic equations or vocabulary, a change in position over a change in time is really just saying velocity. So if you calculate the change in position over the change in time, or you look at the slope of a position versus time graph, you will get its velocity at a given point in time. Now, for the velocity versus time graph, the setup is going to be that, again, time is on the x-axis and velocity is on the y-axis. So in this case, our rise over run, or our change in y over change in x, is going to be delta v over delta t. Okay, a change in velocity over a change in time, which really is just acceleration. So if we calculate the different slopes from these graphs, we should be able to make conclusions about their velocity for the position versus time graph and acceleration for the velocity versus time graph. So let's go ahead and get started and chat about what these graphs would look like for different types of scenarios. Let's start with the first one. So if there's no motion for an object, that means it's obviously not moving, and so its change in position would just be no change in position. In other words, your velocity is going to be 0, and if your velocity is not changing, then you have no acceleration as well. Okay, so if we draw our position versus time graph, I'm going to draw the graph portion in black. Here it is. Again, on the x-axis is going to be time, on the y-axis is going to be position, where position is not changing at all. So really, we're just keeping the line at a position of 0 the entire time, because there's no motion. Okay? Just imagine that red line is exactly on the black line. What does that mean for our velocity? Well, as we just said, there's also going to be no velocity. Oops. Okay. So again, in this case, velocity on the y-axis, time is on the x-axis, and since there's no change in position, the velocity will also remain at 0 the entire time. Okay, hopefully that one's pretty straightforward. Now, when we're talking about a positive constant velocity, that means that our velocity is going to be positive, so positive v, and since it's constant, okay, when there's a constant velocity, that means velocity is not changing. In other words, our acceleration is still equal to 0. Okay, so I'm going to go ahead and draw my position versus time graph. So again, position is on the y-axis, time is on the x-axis. Since it's a positive velocity, that means that our position is changing over time. So if we're starting our position at 0 and we are increasing our velocity or increasing our position over time, what that would look like is just a diagonal line going up, which makes sense, right? It means that at time equals 0, we're at 0, but at time equals 1, we are moving position. We're changing positions in the positive direction, which corresponds to a positive velocity. Now, if we take the slope of a diagonal straight line, like the one over here, what would that look like on our velocity versus time graph? Okay, here's a setup. Well, because we have a diagonal line pointing up, if I was to take the slope of this line, it would just be a positive value. Okay, like for example, it could be that the slope of this line is positive 1. Okay, because it's going up over time, which means it's going to be a positive slope, and it's it's staying constant, right? The rate of change over time is the same. So every second that passes, it's going up like one position. The next second's going up another position. So that kind of change over time is staying the same, and so our velocity is just going to be a horizontal straight line at that slope value, okay? Okay, if we're moving on, now we're doing a negative constant velocity. So that's going to mean that obviously our velocity is negative, okay? Our change in position will be going in the opposite direction. It is still a constant velocity, which means that our acceleration is equal to 0. And then in this case, here, in this case, our position might be starting from a positive value and going down. It can also be starting at 0 and going negative. It's just that our position's moving downward instead of moving upward, right? As time goes on, your position is consistently changing by the same amount, okay? So again, if you take the slope of a line that looks like this, what that should give you is just going to be a horizontal straight line at a certain value, whatever the slope is, but in the negative direction. Okay, so if I look at a line like this, it could be like, oh, the slope is -1. And so the entire time frame, that slope is always going to be -1. That change in position over change in time is constant the entire time. Okay, so that's why the V line stays the same. Velocity line is constant at that negative value. Okay. Now, before I move on, if you look at the 3 different velocity versus time graphs that we have drawn, you'll notice that they're all horizontal lines. If I was to take the slope of those lines, what would the slope be? What would the change in velocity over change in time be for each of these? Well, since the velocity is constant the entire time, that's what a horizontal line means. That means the slope is going to be 0, which matches up with the fact that acceleration is equal to 0 for any kind of constant velocity or lack of motion, okay? All right, let's talk about scenarios where the velocity is changing over time. So when it's changing, it could be speeding up or slowing down. It could be speeding up in the positive direction or speeding up in the negative direction. It could be slowing down in the positive direction or slowing down in the negative direction. So let's go ahead and answer these questions. Let's start with speeding up scenario. So if we're speeding up from a positive velocity, the first thing is, what is the acceleration? Well, anytime you're speeding up, the acceleration is going to be the same direction as the velocity. So if it's a positive velocity, then that means your acceleration is also going to be positive, okay? Now, if you're speeding up in the negative direction, again, your acceleration is going to be the same direction as the velocity. So if the velocity is negative, your acceleration is also going to be negative, all right? Okay, so what does the position versus time graph look like for these scenarios? Let's start with speeding up in the positive direction. Okay, so here's my position versus time graph. The first thing is, since we have a positive velocity, that means our position is changing and going in the positive direction. It's going up over time. But because we're accelerating, that means that that position is changing more and more as time goes on. So this would look like an exponential graph that's moving up. Okay, now there's a curve. It's no longer a straight diagonal line. There's now a curve going upward. Because we're accelerating, our velocity is changing as time goes on, okay? And that means our position is changing more and more as time goes on. Just like in our ticker tapes, when you're speeding up, there's more and more distance that you're covering per given time. That's what this graph is representing. As time is passing, the same 1 second, instead of moving one place for 1 second, now we're moving 2 places for that 1 second, and then 3 places for that 1 second, etc. Okay? Now, what about our velocity versus time graph for this scenario? Okay, so I'm going to go ahead and set up my graph. So what this would look like, if we were to take the slope at various points along this graph, okay, so from the beginning, our slope is flat, but if you notice, the slope starts to increase, and I'm just drawing the slope as a little tangent line to the position versus time graph. So the slope starts low, and then it increases steadily over time. So in other words, let's say the slope at the beginning was just 0, but then as we moved forward another second, the slope maybe became 1, and then maybe it became 2, and then 3, etc. So our velocity versus time graph is going to look like a straight line going up, okay? Again, we're taking the slope from our position versus time graph at various points, and those numbers will then correspond to the velocity values on our velocity versus time graph, because again, velocity is the slope of position versus time. All right, talk about speeding up, but in the negative direction. So obviously this means that we're going to be moving downwards. Our position is going down, but it's going down more and more as time goes on, okay? So first let's just set up our graph over here. So distance over time. So ultimately our line is moving down, but it's going to be speeding up as it's moving down. So in other words, as time goes on, we're going more and more in the negative direction. So this one's a little tricky, but it's going to look like this. If you think about it, again, our decrease is slow to start, but then as more and more time goes on, you'll notice that your position is shifting in the negative direction more and more, okay? So that shows us speeding up in the negative direction. Now, the velocity versus time graph will look like this, okay? Velocity over time. So again, I'm going to take the slope at different points in time, so our slope will start pretty flat at 0, okay? And then as we move down, the slope starts to increase, but in the negative direction. So maybe it starts at 0, and then it becomes a slope of -1, and then it becomes a slope of -2, and then -3. And so our velocity versus time graph is going to be a diagonal line pointing downwards. All right. Finally, let's talk about the motion graphs for slowing down in the positive or in the negative direction. So anytime you're slowing down, your acceleration is going to be the opposite sign as your velocity. So your velocity is going to be a positive value, your acceleration is going to be a negative value, okay? And then if your velocity is in the negative value, your acceleration is going to be the positive value. So what will these position versus time graphs and velocity versus time graphs look like for these scenarios? Okay, I'm setting up the graphs. Okay, so if we're slowing down in the positive direction, that means we're ultimately still moving in the positive direction, but our slope is going to get lower and lower as time goes on. So what that's going to look like is we're going to start with a strong slope to begin, and then it's going to slow down. Okay, as you can see, it's starting to slow down as time passes. So how do we translate this to a velocity versus time graph? Well, to start, we start really steep, which means we have a high slope, maybe a slope of, I don't know, 4 or something, okay? And then as time goes on, our slope gets more and more mellow, right? And so we start from a slope of 4, and then maybe it's 3, and then maybe it's 2, and then eventually it becomes 0. And so our slope our velocity is ultimately positive, but as time moves on, it's getting less and less fast, okay? How about for slowing down in the negative direction? Okay, here's my position versus time graph, and then here is my velocity versus time graph. Okay, so for slowing down the negative direction, ultimately we are going to be moving downward in position, okay? But the amount of change in our position that's going to happen over time is going to slow down. So initially we're changing positions quickly, and then we're going to not move as far per unit of time as time moves on. So what that's going to look like is we're going to start off steep in the downward direction, and then it's going to mellow out as time moves on. Okay, so what this means is initially we are going to have a very strong negative slope, and then the slope is going to slow down as time moves on until it becomes like 0. Okay, and so if you take a look here, maybe we'll start with the velocity or slope of -4, and then it mellows out to -3, and then -2, -1, 0. Now, if you take the slope of the velocity versus time graphs, it should agree with whether the acceleration is positive or negative. So for example, when I'm looking at this slope of this velocity versus time graph, it's going to be a positive value, which matches up with the fact that the acceleration is positive, because again, the slope of a velocity versus time graph is the acceleration. Same with this scenario. It is ultimately a line moving up. It's a positive slope, matching with the positive acceleration. And then the opposite for the negative acceleration.